Good day. Carrie Lisse here from the New Horizons Science team to talk to you about the ices that we see in MU69, also known as Arakoth, I'll use both terms interchangeably, and Pluto. And specifically, I'm going to talk about the origin and thermal stability of Pluto's and MU69 ices, or how Pluto got its hypervolatile ices while Arakoth has not. I'm going to start with inclusions first and then illustrate them for you later. Take-home message and questions from this study. 1. Methanol in MU69 is superabundant versus short-period comet and similar to distant centaurs. At levels versus H2O seen in molecular clouds or hot cores, there's something extraordinary about the amount of methanol in Arakoth. A superabundance versus SP comets argues for presence of pure methanol ice in all KBOs, including Pluto, and distant unheat-treated centaurs. 3. Small normal abundances of methanol in SP comets only as alloyed minor species in amorphous water or crystalline water ices. 4. Hypervolatiles were never incorporated in small KBOs unless the protoplanetary disk was mid-plane optically thick. In other words, it was extremely cold extremely early on, and these small bodies formed quickly. Can this explain the striated pit fields on MU69's limb as hypervolatile loss upon protoplanetary disk mid-plane clearing? And 5. Hypervolatiles, CO, N2, and CH4, are present in the largest KBOs. This implies less than 10 million year formation time, as I'll go into more. They had to form quickly while there were still hypervolatiles in the small bodies that they formed out of. Or was there a hypervolatile nebular gas source during formation? Did Pluto form quick enough, for example, that there was still gas around, hypervolatile gas, that it could accrete once it got big enough and hold on to with its exobase? Or were the amorphous water ice sourced hypervolatiles in a fully differentiated Pluto? What does this mean? It means that the small bodies had lost their hypervolatiles by the time Pluto lazily got formed, much later. But there was enough hypervolatiles left in small impurity phases in the amorphous and crystalline ices, water ices, that was enough if you had totally melted Pluto through and through that the really light hypervolatiles come to the surface and see what we saw on the surface of the largest KBOs today. Okay, that's a mouthful, but there's a lot of very exciting results we're going to start talking about. And we're going to probe into the history of these bodies. So if you'd like more detail of this, if this talk is too fast or misses some equations, some details, please check out our brand new paper, Lisse, Young, Cruikshank, and Out 2021, on the origin and thermal stability of Pluto's and MU69 ices, coming out very soon to a store near you in the Icarus MU69 special issue. And there's the DOI down bottom. Our journey in this investigation begins with asking if 2014 MU69s, aka Arakoth's, surface would produce detectable gas from the NH flyby. We tried to detect a coma or any activity around this object, and thinking maybe it's acting like a very distant comet orbiting the sun at 45 AU. And so we did our best job looking with the Lisse instrument and looking with the Alice instrument, and even trying to count dust particles in a coma that would be surrounding MU69, and we found nothing. The most stringent constraint we got from Alice Lyman alpha spectrometer, we looked back towards the sun and we looked for any sort of absorption, and we didn't see anything. And we didn't see anything down to 10 to the 24 molecules per second of H atoms coming off. And we can translate that into other species, would even be smaller. So moderately stringent limit compared to what a short period comet at 1 AU, which is about 10 to the 27, 10 to the 28 molecules per second, then put out 45 AU distant, or 1 over 45 squared amount of solar radiation hitting its surface. It's not terribly constringent. You would expect a short period comet to be less active than that. So, but it did tell us right away that we didn't see anything. This didn't look like an active body. We then made the next step. We tried to ask ourselves, okay, what if the surface of Arakoth was totally covered in an ice? And ice being any of the ices that we expect to see in bodies, icy distant bodies or primitive bodies in the solar system. Everything water and methanol, HCN, and ammonia to CO2, but also hypervolatiles, things that we see on the surface of Pluto. We knew from the Pluto flyby in 2015, like nitrogen and CO and methane. Other species where we've seen in minority fractions in the coma of short period comets, like argon and O2, and ethane and propylene and benzene, things like that. We just basically threw it all into a mixed mass, and we did a simple calculation. If you can measure the heat of sublimation of an ice species versus temperature, you can predict what its vapor pressure should be. And since we know about what the temperature of Arakoth is at 45 AU from the sun today during our flyby, then we can figure out what the vapor pressure for the ice should be. And you see in this plot, in this figure, is that what you create are a series of self-similar curves that have the structure of vapor pressure goes as a constant times the exponential to the negative heat sublimation divided by kT. And these curves all have a very steep rise at a characteristic temperature when H sublimation over KT starts to be appreciable. And then they'll asymptote out as KT, as temperature gets very large. And they just get shifted over into higher and higher temperatures depending if heat and sublimation gets larger and larger. And these ices fall into three different curves, which we're going to talk about over and over and over again. And they're color-coded here as the reddish curves in the upper left, the bluish curves in the middle, and the greenish curves in the lower right. The ones we call in the upper left we call the hypervolatiles. Those are your carbon monoxide, your nitrogen, your methane, your argon, your oxygen. These are species that in the ice phase are what we call molecular solids. They only held together very weakly between the different subunits, between the individual CO molecules in this ice, by van der Waals forces. They're very easy to boil off. And that's why they're cryogenic ices, and they boil off very rapidly at 10, 20 degrees Kelvin. We're going to talk about these a lot, and the most important thing, take-home message to think about these, is that we know they're on Pluto. We don't see them at all. We don't see any evidence for them in MU69, yet we know that they're also simple primordial molecules, and they should have been around at the very beginning of the solar system. We have the metastable or the mesovolatile species, what I think of as the larger organics, things like ethane and propane and benzene, and even CO2 to a moderate extent, are moderately volatile, and they'll start corking off and start evaporating rather rapidly, around 40, 50 Kelvin into vacuum. And then you have what I call the refractory ices, ones that are held together by actually relatively strong bonds, milli-electron volt bonds due to hydrogen bonding, actual semi-chemical bonds between subunits. The prime example of this is water, where one hydrogen and one water molecule actually have an electron connection or a bond to an oxygen on another molecule. There actually is a bit of a chemical interaction, and these are strong ices. It takes a lot of energy and high temperature to boil them off. Water is the most refractory of all, but also included in this group are methanol and HCN and ammonia. So gathering all this information together, plotting these curves on this plot, and then putting the New Horizons ALICE upper limit of 10 to the 24 molecules per second onto this plot, which you see in the horizontal dashed line at about vertical axis about 10 to the 3, you can see that we would have seen the hypervolatiles at the temperature of 45 K, as you see the vertical dashed line, Arikoff today. And we just, so we would have predicted a vapor pressure from the hypervolatiles about 10 to the 11th, 10 to the 12th on this plot. Many, many orders of magnitude higher than the limit we can set with ALICE. So we know there are no hypervolatiles on the surface of MU69. There are not even any, the mesovolatiles, maybe. The refractories, no problem. They could be there existing just fine and stably. So what we've learned from this is there are no hypervolatiles on MU69, but we can't say too much about the other ices from this experiment. Well, then we decided to go a little bit more into detail. We thought about the problem some more, and we realized that you can ask a more stringent question. You can say, okay, we've gotten the vapor pressures. We know the temperature at which the materials are coming off, because once you start boiling off an ice, it stays around the temperature at which it's boiling. Think of how water stays about 100 degrees C when it's boiling from a pot at 1 atmosphere on the Earth. And then we said, okay, how long does it take at a given vapor pressure for that ice to be exhausted? If it was ever exposed to the surface, if it was ever exposed in this object, how long would it take for it to start disappearing on molar quantities? And then what we could do is make the exact same plot, but a little more detailed here. Now what we could do is draw a dashed line for how long it would take for 1 year, what rate at which 1 year all the ice would disappear, or 1 kiloyear, or 1 megayear, or 4.6 gigayears. We draw those same self-similar curves, and we find out the temperature of our body. So for example, we have MU69 at 45 degrees LTE, but if it's the summer solstice, which most of, because MU69's peculiar orientation, which we observed it now, is all the sunlit side, it even goes as high as almost 60 degrees Kelvin. And you can quickly see, given our curves, and given these vertical dashed lines at LTE if we're being kind, or summer noon if we're being harsh and more demanding, that almost all the ices on MU69 surface would be gone in 4.5 billion years, except for the refractory ices, HCN, methanol, and water. They're just not, we don't expect anything else. To test this model and make sure we know what we're doing, also on this plot is Pluto. The pressure of Pluto is the orange horizontal bar you see here, at about 10 microbars scaled. And if you track the curves on this, at 10 microbars, you see that the hypervolatiles can last, and Pluto's surface temperature is about 35, 40 Kelvin, depends on where you are. And you see that the hypervolatiles even can be stable at 4.6 gigayears, as long as there is enough pressure to hold them down, and that 10 microbars is enough to make the hypervolatiles both solid and gaseous. And that is exactly what we see on the surface of Pluto. We see many fields of CO and methane and nitrogen, especially in Sputnik Planitia for the nitrogen. But we also see these species in the atmosphere. So we see the hypervolatile ices are metastable on the surface of Pluto. So noting this, that we actually have, if you will, this ground truth or this physical reasonableness of this analysis, we went ahead and started asking some more questions about the thermal history of these ices. The first question we asked is, where in the solar system would these ices be stable on gigayear timescales? And the short answer is, here's a plot or a picture of our solar system with the planets all decked out from Mercury near the sun all the way out to Pluto in the Kuiper Belt. And one can simply put on this plot where I gave you temperature. We can go T is equal to, goes as 282 over the square root of R. And you can figure out where these different ices would start evaporating very quickly. And starting from the outside in, you can see that in the Oort cloud, very distant, we're talking hundreds of AU out, hundreds of thousands, hypervolatile ices can be stable. But once you get into the Kuiper Belt, you move into 30, 40, 50 AU from the sun, you only expect the refractory ices stable, as I mentioned before, over gigayears. Moving as close as Saturn, and even the refractory ices are all evaporating, except for water ice. And water ice is transforming from amorphous to crystalline water ice. And then once you get into the asteroid belt and where we live, where the comets come in and pass close to the sun, even the crystalline water ice sublimates and everything starts disappearing from your icy body. Okay, so how does this thermal stability picture jive with what we saw at Arrokoth using New Horizons? Well, in this figure, I'm showing you the MVIC and Lisse spectrophotometric data that we got from observing the surface of MU69 during the flyby. And those are the points you see on the left, the circles and the diamonds and the stars are the MVIC data. And the Lisse data is in the little black jagged points. Superimposed on top of this are the spectra of Pholus, a very distant, very inactive, the reddest known centaur, and a Plutino, 2002 VE95 in yellow. Pholus is in red. And you see that there's a gross similarity between all three of these spectra, which is very interesting. It's saying that the different classes of small bodies in the outer solar system, be they a centaur from the scattered disk, be they a MU69 is cold classical, or they be a resonant Plutino, all seem to roughly have the same surface spectrum as long as they're small. What do we see in the surface spectrum? We see definite evidence for methanol and tholins. We see hints and suggestions there's also water ice from the turnover of the continuum. What we don't see is a very strong, simple, direct absorption of water, which we were hoping to get, but we don't see that very much. So bottom line, we can say it looks like there's a lot of methanol and tholins on the surface of this object, and we think there's also water here as well. Okay, going back to our stability curves, we would have predicted, if you look, the two most stable ices, I'll remind you, refractory ices are water and methanol, which is what we see best indications on MU69. But then in the lower left, we can ask ourselves, how come there's methane and nitrogen and CO on Pluto, which we see in abundance? Why is it there? I gave you the answer that metastable, it can be there because there's an exobase, because Pluto is large enough to help support an atmosphere, that those ices can be stable. But we have to ask the question, how did they assemble there in the first place? Okay, I've just promulgated the idea that we do not see the hypervolatiles in MU69 today. I quickly pulled out the idea of MU69 being a cold classical, the blue dot in the bottom. VE95 is this yellow dot, it's a Plutino, along with Pluto. And then a scattered object like JFC 67P, the target of the Rosetta mission, or Centaur Pholus, would be coming from the third population of Kuiper Belt objects. It's important just to remember these different populations, yet we were seeing similar behaviors in terms of their surface spectra across, as long as they were cold and in the outer part of the system. The short period comets get changed over, we think. So, speaking of the short period comets, it is important to note that in Halley, in Borrelly, in CG, and other comets, we do see small minority fractions of hypervolatile CO, N2, and methane, in the order of a fraction of a percent to maybe as much as a percent or two, versus water. They are there. They aren't there in large amounts, in vast amounts of pure ices, but they're there in small amounts versus water, which makes us believe that they are actually trapped in water, or they're, if you will, either as impurities or either alloyed in amorphous water ice, or as a clathrate or in a crystalline locked in a crystalline lattice in crystalline water. This figure is also to try and show you the similarities we see in many of the morphologies of these different bodies. 3 comets on the right and Arrokoth on the left. Arrokoth is about a factor of 10 bigger than these bodies. I mean to remind you of that. But still, the bilobate morphology looks similar, giving us good arguments, good belief that there is a common origin for all these, i.e. that the Kuiper belt objects get scattered in, self-scattering in the Kuiper belt, into the Centaur region, and the Centaur region they eventually spiral into the perturbations from the outer planets until they become short period comets. So they're all genetically related. If this story is true, then we should expect to see this ice behavior following those curves of thermal stability and instability. Well, here's some evidence for that. In 2009, Jewett published a study where he looked at centaurs at different distances from the sun. And this study was also followed up in Lee 2020, which verified the distant inactivity. And basically what Jewett found was that only centaurs within 10 AU of the sun seemed to be active. So his conclusion from this was that not that there was CO or CO2 driving this activity, because they would have been active even out to 20, 30 AU. Little bits, but still active. But instead, what was going on was he seen behavior driven by amorphous to crystalline water ice changeover and phase transformation. And what's happening then is that as you're going from amorphous to crystalline, you are going to a smaller, denser phase of water which can hold fewer impurities. And so that transformation not only will release heat, but it will also release impurities and cause some activity. So this is, if you will, a connection between the KBOs and our short period comets, which we use as proxies or to understand the KBOs better. Why do I say that? Well, just to make sure we on hypervolatile ices aren't hiding down deep in Arrokoth, that we're talking, we've seen the surface, but we haven't really probed down to the very center, kilometers deep from the surface. We've looked at comets that have broken up. Okay, these are their distant kin, if you will, or their old descendants. And when they break up, like 73P was seen to do in 2005 and 6, or 17P Holmes in 2009 and 10, or 103P Hartley 2 when it was flown by the Deep Impact mission in 2010. When we look at these objects that are either broken up or just recently disrupted, or in the case of Hartley 2, at their very last legs, very, very small, only the smallest remnant of the original body is left. And it is basically emitting very strongly its guts in big pieces and chunks. We do not see large amounts of CO, N2, or methane. There is no evidence that we know of, observational evidence, that there are hypervolatile ices hanging around very deep inside of these bodies. It's just not there. So this gives us confidence we know what we're doing. We're talking about the fact that hypervolatiles are gone in large quantities in primitive icy solar system bodies. And we even have a counterexample, and this is what's really cool. In 2016, an object called C-2016-R2 was discovered, and it was the strangest comet that I've ever heard reported. And that's quite a saying, because there's been a lot of very interesting comets. And what was reported for this object was that extremely large amounts of CO and N2 were coming from it, but no water. And no water, that's very strange. Everything we see in comets, the coma is basically water plus a little bit of seasoning, if you will. That's a little rough. It's usually water plus maybe a fifth CO or CO2. And that's basically what a coma is. And then the rest is seasoning, if you will, or a small percentage amounts of different species. This one showed huge amounts of CO and N2 and no water. Well, that's almost exactly what you would expect for an object that had its hypervolatiles and was actually actively throwing them out, and due to sublimative cooling, was keeping the water solid and refractory. Another way to put that is the same way that when you try to boil a pot of water off and you can't raise it above 100 degrees C on your stove, until all the water is gone, you can't raise the temperature of an object that has got a lot of CO and N2 still in it as you're boiling them off until they're all gone. And if you go back and look at those curves I was showing you before, that keeps the object somewhere around 20 Kelvin or so. 20 Kelvin is way below any sort of vapor pressure curve of water. And so water is acting literally like rock. It's as strong and as stable as rock in the outer solar system. So 2016 gives us a wonderful and very interesting counter example of an object, the one object we know that looks like it is darn rich in hypervolatiles. Now we can ask a really quick question then. How come this one's different? Why did they survive in it? Well, the only way we can understand that, given our thermal stability curves, is this an object that must have formed very quickly in a solar system and then gotten thrown out into the Oort cloud, where it resides today, in order to stay cold enough to keep those hypervolatiles. Now, a corollary of this is that once the midplane clears, or we like to say once morning and sunrise came to the Kuiper belt, then suddenly all the temperatures changed. They rose, they spiked. And so you could have gone from a midplane temperatures about 20 Kelvin, which we think we see when we look at other protoplanetary nearby disks like TW Hydrae, and we look at our models. We think that it would have been rather cold, and I mentioned 20 Kelvin is enough to keep your hypervolatile stable. You see over here in the upper plot in the upper left. But once morning comes to the EKB, suddenly you're going to go up to LTE of 40. You're going to go to summer temperatures of 60, noon temperatures. And you're going to drive your hypervolatiles off very quickly. So this would give you some massive sublimation event that happened early on in the history of MU69. Didn't happen for R2, but happened for MU69. And that very likely could drive what we see are these little pit chains, these linear chains of it looked like associated depressions. Pits is a strong word if you're a geomorphologist, but what could be sublimation pits and don't look like craters. And we see them all over Arakoth. So, and because Arakoth has stayed at 45 AU after its formation, roughly stable temperature system, and after this morning arose, then we could be seeing the remnants and the leftovers of this morning event, but nothing afterwards. This next plot shows why do I believe those temperatures. I just threw out some numbers. Well, I mentioned one is that TW Hydrae has been directly measured and looked at in the submillimeter, and temperatures of the order of 15 to 20 Kelvin have been measured at Arakoth's equivalent distance from that star. As well as a very recent model put out in 2019 by Muzas et al., studying Jupiter's formation in the vicinity of the amorphous ice snow line, trying to see if you can make Jupiter out of a whole bunch of amorphous ice mixed Arakoths. And they start out with models as cold as 5 Kelvin as its location, even colder than what's measured in TW Hydrae. So the numbers we're talking about, 5 to 20 Kelvin or so, seem to be very reasonable. And so it's very reasonable to expect that hypervolatiles could have first formed and associated into Arakoth. Okay, so here's that argument again. I kind of preceded it, but I'm going to say it again here in this, I think, this summary slide. Pluto shows that carbon monoxide, nitrogen, and methane hypervolatile ices were available in the Edgeworth Kuiper belt. And again, how? We know that MU69 should have lost its hypervolatiles, if you look at our thermal stability plot, within a few million years. At most. If you're being generous, 1 million years. Once morning comes to the Kuiper belt. So, your first conclusion, you can make Pluto really fast while the hypervolatiles are still very happily inside our very small KBOs. Those small KBOs accrete rapidly, build up a Pluto very quickly, and then Pluto differentiates, and those hypervolatiles all come to the surface. Pluto is big enough and has enough gravity to hold those hypervolatiles into an exobase, and everything's stable, and Pluto evolves slowly but surely to see the object we see today. Number 2 possibility. Pluto forms a bit more slowly than the first than 1 mega year. That's kind of quick from a lot of the models. Remember, the Kuiper belt, we think there was enough mass in order to make snowballs, if you will, and dwarf planets. So what we call the small KBOs and Pluto and Charon and the like, and Eris, but not the large bodies that we see like the giant planets, which we think form very fast because the rate of growth should go roughly as the density squared of the material. Just density squared from it takes collisions between two different small pieces of stuff in order to form and aggregate larger pieces. So you're trying to form something quickly in an undense region of the solar system. So that's probably not so likely. You'd think it'd form a bit slower. So let's go to number 2 possibility. Pluto formed within the first 10 million years in a system with the nascent sun, a accretion disk, and a protoplanetary disk that's still filled with gas. So Pluto forms its tough rocky bits at center. It's forming out of Arakoths that have lost their hypervolatiles, but it forms rapidly enough, not too rapidly, but rapidly enough, and gets big enough that it can clothe itself in hypervolatile-rich gas. This gas is the stuff that escaped from the Arakoths, but is still in orbit around the sun. And so then Pluto grows big enough, it can trap these hypervolatiles. It grows big enough that it can create a 10 microbar exobase at the surface, and then those ices are stable. Number 3 is Pluto took its bloody time to form. It took forever. And it forms very late. It forms 100 million years or so, let's say, or even a billion years. So none of these things happen. The hypervolatiles actually come from the minority, tiny, tiny little phases, what's left over in the very robust and stable methanol and water ice phases. There was enough hypervolatiles, maybe the 0.5% level, that if you totally melt Pluto through and through, you make them out of comets, what we know about comets today, and Glein and Waite wrote on this in 2018, that if you were to totally differentiate Pluto, make it out of what we know of comet recipe material today, you could have created the hypervolatiles we see on the surface of Pluto. The same analogy as how you put the ocean water on the surface of the Earth. Earth is made out of asteroidal rocky materials that have a few percent water. You put them all together, you manage to melt them, differentiate them. All the water boils in, comes out from the interior and boils up to the surface. Some of it stays stable on the surface. And basically it's a density gradient. When you differentiate, you're bringing all the light volatile material to the surface. And so Pluto's equivalent of that is the hypervolatiles. Okay, that's actually point number 4. Number 3, I'm sorry, this slide got updated as I talked, is Pluto formed late, but in streaming icy Oort pebbles actually bring in the gas and the hypervolatiles. So Pluto forms hypervolatile pore, but its last surface clothing is rich in hypervolatiles. And so this is the, if you will, the new pebble accretion model. And this is something we haven't explored too much, but we have added it because we think it's another possibility. Okay, that's a lot. I hope this wasn't too rambling. And I thought it's very interesting to realize what you can do from very simple model-independent thermodynamic calculations with the constraints you can put on things. And the whole reason for this talk, if I haven't said it already, is to try to get people to think, where do you go from here? How do you do more time-dependent, more rigorous modeling? But given these very simple statements, like we know the hypervolatiles are not there in MU69 today. So let's get back to the Pluto system. There's actually some other very nice implications we can make and deductions we can make for the Pluto system. Pluto's airless low-gravity small moons, which are not too different in size than MU69, should only have refractory hydrogen-bonded ices in them, just like Arrokoth. Pluto itself should have large amounts of methanol bedrock ice, as well as water ice, which came from its Arrokoth formative block units. So we've not really considered this very much. There should be lots of methanol. When I've asked the Lisse team if they could find methanol, they said it's very hard to do with all the methane on the surface of Pluto. They have very similar absorptions in similar places. So, but they're still looking carefully for the few differences and trying to see if they can get really good signal noise in some places. We also need to consider the Pluto-Charon forming impact. Hypervolatiles, if the impact that formed Charon was so severe that it totally removed hypervolatiles from the surface of Pluto, and most of the models say it was a very severe event, then if the Charon forming event happens after 10 million years, then all the hypervolatiles have to come. There's no way, they can't source them from the planetary disk or surrounding nebula, or even icy pebbles. They have to come from the interior of Pluto. So if the Pluto-Charon forming event happens very late, that would argue that the hypervolatiles are coming from the interior of Pluto. It seems to favor hypothesis number 4. However, there's the clathration ratio problem. If we like hypothesis number 4, and we've argued ourselves into it, we would expect polar CO to be much better trapped in water ice crystals. That it actually has the same reason the hydrogen bonding works well, is because there's ionic displacement in the subunits in water ice, is you would expect CO, which has a dipole moment, to actually bind better, and it does by a factor of a bunch, than apolar N2. Yet when we look on the surface of Pluto, we see much more nitrogen than we see carbon monoxide. So there's something wrong there. So it's hard to understand exactly how one could simply source it directly from the interior just by assuming that everything was trapped originally in water ice phases. However, there is some question or possibility that actually when hypervolatiles are trying to bubble up through the surface, that they can get retrapped preferentially. The CO actually likes to go back into the water ice and it can't make it out of the interior. And Kamada et al. 2019 have argued this persuasively. And that maybe that, yes, you're still coming from the interior, but you didn't come uniformly, you just didn't come en masse. There was a filtering effect. Okay, that was a lot, but I think this is very exciting. So again, we're back to the conclusion slide, and we're back to the plug at the very bottom for this new paper, brand new paper that we've just put out. And again, I want to reiterate the take-home messages and questions from this study. Methanol in MU69 is superabundant. We have to explain it. We can explain it with thermal stability of refractory methanol ice. We don't see it in short period comets, which means that methanol ice somehow has to disappear as KBOs turn into centaurs and centaurs turn into short period comets. And we think it happens when the centaurs turn on inside 10 AU from the sun. The small number of abundance of methanol in SP comets is there. We do see methanol in short period comets, but it's at small levels versus water, few percent, which is telling us it's most likely in water ice phases as impurities and clathrates. Hypervolatiles were never incorporated in small KBOs unless the protoplanetary disk formed optically thick. And also it was cold in the midplane of the protoplanetary disk, and these bodies formed quickly. And we think there's evidence from the surface morphology of MU69 that can explain or show that this actually occurred. There was massive sublimative loss at the very early stages of MU69's life. And I mentioned the pit chains. It also could be due to some of the wrinkling and crumpling we see between the subunits in the monkey bread on the larger lobe. So mass loss could very easily have happened from what we understand of the surface. Finally, hypervolatiles are present in the largest KBOs. So then you can ask the question, as I went in some detail, does that mean most likely they either formed really quickly or they have been sourced from interior material on these objects? Okay, I'm done now. If you like this work and this discussion, there's even more in our paper. We have a really good time discussing it. And very much, if you would like to talk to us more about this work, or you'd like to extend it, or you want those curves, the data from those curves, read our paper and contact us by email. Thank you very much for your attention. Good night.